This is the video for section 8.4 notes, slides 28 through 31. All right, so in section 8.4, we are talking about work. All right, so work is a topic that is covered in physics, but this is something that could show up on the AP Calc test. All right, so work is talking about applying a force to something over a particular distance. And so we are going to be dealing with work in two different ways. Okay, one way is where the force that is applied is of a variable amount, or the distance that is moved is a variable amount. All right, so there's basically two types of examples that we're going to be dealing with. The first one is with a spring. All right, so you should know that Hooke's law for spring says the force that it takes to stretch or compress a spring x units from its natural length is a constant times x, or in other words, F is equal to kx, where k is a force constant, or sometimes known as the spring constant, depending on how the spring is constructed. All right, and so to calculate work, we are going to integrate the force function with respect to x. All right, where x is the distance. Right, so okay, what we're dealing with here, if F is equal to kx, let's draw a graph of a force function, right? Now, if the force function is k times x, this is just a line with a slope of k and a y-intercept of 0. So we actually have this function, right, which is really pretty easy, where F is the y-axis and x, or the distance, is the x-axis. All right, and so what does the distance refer to? So if I have a distance of x here, that refers to the distance that the spring is stretched or compressed from its natural length. All right, and so if we think about this, why would we integrate this? Well, let's think about integration. Remember, integration is finding the area under a curve. So area is going to take the x value and multiply by the y value. So if I multiply a force times, I guess I shouldn't use an x there, times a distance, right? That is when I'm getting work, force times distance. And so we are going to be integrating the force function, all right, from A to B. Now, A to B, what does that mean? Well, A is the starting length and B is the ending length. But remember, okay, if the spring is not stretched or compressed at all, then its length is considered 0. It is not considered like if a spring is 5 inches long, then it's 5 inches, right? The natural length of the spring is considered a distance of 0, all right? And so that's what we're dealing with, all right? So that is where the force is a variable, right? Now think about this. If you have a spring and you stretch it 1 inch past its natural length, right? It took excuse me. It took a certain amount of force to stretch it that 1 inch. Now, if you stretch it an additional inch, it's going to take even more force than it did to stretch the first inch, right? And then another additional inch is going to take even more force than it did the first or the second, all right? And so the idea is that the force that is applied to stretch an additional inch would be more and more and more, right? So the force is a variable, right? And that's why we write it as an f of x function. So the force is a function of the distance that it's being stretched. All right, so a couple examples of this. All right, so number one, a spring has a natural length of 3 feet. A force of 10 pounds stretches the spring to 3.5 feet. Find the spring constant. All right, so very simple. F is equal to kx, right? So k is the spring constant, x is the amount that has been stretched, and 10 is the force, right? So we can say, okay, well, a force of 10 pounds is going to be k times not 3.5. Remember, its natural length was 3, and its new length after stretch is 3.5 feet. So what does that mean? It was stretched by 0.5 feet. All right, and so what does that mean? That means that k would be equal to 10 divided by 0.5. Now, 10 divided by 0.5, that's like 10 times 1 divided by 1/2, so 10 times 2. So this is 20. Right now, what are the units of k? Well, I took 10, which is pounds, divided by feet. So this would be pounds per foot. That's what K would be, right? So 20 pounds per foot is the spring constant. All right. Now B says find the work done in stretching the spring from its natural length to a length of 5 feet. All right. So now its natural length is 3 feet, right? And its new stretched length is 5 feet. So what does that mean? 3 feet would have been 0 feet of stretch, and 5 feet now is 2 feet of stretch. And so the work is going to be found by integrating the force function from 0 to 2, right? And what is the force function? Well, K was 20, so 20x with respect to x. All right, so now I'm going to integrate 20x. So that'd be 20x squared over 2 or 10x squared and evaluate from 0 to 2. All right, so 10 times 2 squared minus 10 times 0 squared is equal to, well, 10 times 2 squared, so 40. Now, what are the units? Remember, I'm taking a 20, which is pounds per feet, right, and multiplying by an amount of feet, right? So that would be pounds. But remember, when I multiply by dx, that's another unit of feet. So the unit here is pounds times feet, okay? Sometimes referred to as foot pounds, okay? Now, you might recall in physics, we talk a lot about work in the SI units. And so force usually measured in newtons and distance measured in meters. And so we know of work as the unit Newton times meters, right? Or Newton meters. All right, now, find the work done in stretching the spring from a length of 4 feet to 5 feet. So remember, 4 feet is a stretch of 1, and 5 feet is a stretch of 2. So we're going to be calculating the integral from 1 to 2 of 20x dx. All right, and so now, once again, 10x squared from 1 to 2. So 10 times 2 squared minus 10 times 1 squared. All right, 10 times 2 squared, of course, is 40. Minus 10 times 1 squared is 10. So 30 foot-pounds, right? So think about this. To go from 0 to 2, it took 40 foot-pounds. But to go from 1 to 2, it took 30 foot-pounds. So it only took 10 foot-pounds. So it took triple the amount of work that it did to go that extra foot of stretch. All right? So that is work with a spring, right? So that's where the force is a variable. All right, but now, okay, on slide 30, we're talking about a situation where the distance that something is moved is a variable. All right, so how can you imagine that? Well, now we have to deal with something that isn't a solid object. So for instance, if you move like a book or a desk or whatever, all aspects of that solid object have to move the same distance, right? Otherwise, the object is no longer in its shape. All right, so water is a great example of an object that as you move it, okay, it could be in a different shape or it could take a different form. All right, so what we're doing here is we're lifting water. So the example that we're going to be dealing with is, let's say that we have, I don't know, like a tank of water. All right, so we have a tank of water. All right, and what we're going to do is we are going to insert a tube, let's say, into the tank of water, and we are going to like suck the water out of the tube, and the water is not going to be going into this aquarium. It's going to actually leave the aquarium, and it's going to get lifted to some other thing, right? So now, it could be another, reservoir of some sort, but the key is that we have to do work to get it from this tank up to this level. Now, what happens after it reaches this level is we don't really care about. Let's say it goes into this thing and then it goes through like a waterfall or something. Gravity is doing the work to move the water now. Okay, we had to do the work to get it up to this level in order to do whatever else was after that. All right, so what we're going to do, all right, we have to think about this in terms of slabs of water. All right, so first thing I want you to do is I want you to imagine taking this aquarium and cutting it horizontally. All right, so you cut it horizontally, and in this case, you're going to get like a rectangle, right? I mean, the way I drew that picture, but it could be some other shape. It could be a cylinder or whatever. All right, so we cut this. Now, this is a slab. So let's say that this is two-dimensionally. First of all, it is a rectangle. So first of all, we consider area, right? So area of a slab. Well, it's going to be whatever the area of the shape is. In this case, it's a rectangle, right? So we're going to say A is going to be the area of the slab, okay? Next, well, if we apply a thickness to it, right? Now, it's infinitely thin, right? But let's say we apply a thickness like a dy, right? So we now get a volume of a slab. So we're going to take the area of a slab, and we're going to multiply it by its thickness, right? So this is now a volume, right? It's a volume of water, okay? But now, we need to think about weight. How do we think about weight? Well, weight is a volume multiplied by a density, all right? And so, how do we figure out the weight? All right, so the weight of water, okay, is going to be the volume of water multiplied by its density, all right? So the density of water, right, and that's what we're going to be dealing with in all these examples, all right, is going to be 62.5 pounds per cubic foot, all right? And so when you think about it, if you're taking a volume, which would be in cubic feet, and you multiply by pounds per cubic foot, your result is an amount of pounds, right? Which is what we want, right? That's what we're dealing with, weight, all right? So you have to figure out, number one, the weight of a slab. So you're going to take the area of a slab, okay, so whatever the shape of the object is, you're going to multiply by its density, 62.5, right? You're going to multiply by its thickness, which in our case is going to be dy, and then you're going to have a weight, okay? So now, what you're going to do is you're going to find the distance needed to lift a slab to the desired height. All right, so now what I want you to think about is dy represents all of the infinite number of slabs of water in this tank, right? So there's a slab at the very bottom, a slab above that, a slab above that, a slab above that. There's an infinite number of these, right? Because remember, the dy, the thickness, is infinitely thin, all right? And so then you have to ask yourself, how far does the slab need to travel? All right, so let's say that we have a total height of 6 feet. All right, now the tank, let's say, is 4 feet deep. All right, how far does each individual slab have to travel? Well, each individual slab is y feet or y units or whatever off the bottom of the tank, right? So how far does it have to travel? Well, from where it is all the way to the top would be 6 minus y, right? So in this case, okay, the distance needed to travel would be 6 minus y, right? So that's the distance. Now, remember, the distance in this case is a variable, right? Because a slab at the very bottom has to travel 6 feet, but a slab at the very top only has to travel 2 feet, all right? So what we're going to do is we're going to integrate the weight of a slab times the distance needed to lift to the desired height. So we're going to take the area of a slab multiplied by its thickness, which is dy, multiplied by its density. Remember, area of the slab times dy, that is the volume, multiplied by the density, so 62.5. And if it was a different type of liquid or whatever, then we would have to have some other different density. And then multiplied by the distance needed to travel. So in this case, 6 minus y. Now, we're going to integrate that from what to what? Well, where is the lowest slab of water? That would be 0. Where is the highest slab of water? That would be 4, right? And so then we want to carry out this integral. Now, remember, I put the dy here, but we would probably just move that to the end. And then we would move any constants out front in order to integrate. All right, so let's try another example here. All right, so it says a vertical cylindrical tank, it should be like a right cylindrical tank, of radius 5 feet and height 8 feet is full of water. Find the work required to pump all of the water over the top of the tank. Once again, water weighs 62.5 pounds per cubic foot. All right, so a cylindrical tank, right? All right, so we have a cylindrical tank here. All right, and it's of radius 5 feet, okay, and an overall height of 8 feet. All right, so it's full of water, and all we're doing is we're taking the water and we are pumping it just over the top of the tank, right? All right, so first of all, what is the area of a slab of water? So now, if you were to cut this tank horizontally, you're going to get a circle, So a slab of water is going to be pi times the radius squared. Right now, remember, specifically the radius is 5, and that is not changing, right? This is not a cone or something, right? So at every location in this cylinder, the radius of a slab would be 5 feet. So we would say pi times 5 squared, or just 25 pi, right? So that's the area of a slab. So now the volume of a slab is very simple. Just take the area multiplied by its thickness, which is just dy, right? So 25 pi times dy. All right, so that's the volume. Now, remember the next thing is the weight. All right, so the weight of the slab is the volume, 25 pi times dy, times the density, 62.5 pounds per cubic foot. All right, so now remember, this is an amount of pounds, right? Because we have 25 pi times dy, that's cubic feet, times 62.5 pounds per cubic foot. So this is an amount of pounds. All right, so now the distance. What is the distance that each individual slab needs to travel? Remember, each individual slab is y units off the bottom. And so the total distance here is 8. And so the distance that any individual slab needs to travel is 8 minus y. So that means something that's at the very bottom of the tank would need to travel 8 feet because its height is 0. But something that's at the very top of the tank doesn't really need to travel at all. It's just 0. All right? Because it's 8 minus 8. All right, so now we are going to integrate the weight, so 25 pi times dy, but I'm going to put the dy at the end, times 62.5, right, times the distance, 8 minus y, and then I'm going to put the dy at the end, right? And we're going to integrate from what to what? Well, the lowest slab of water is at 0, right, 0 feet. And the highest slab of water, well, this tank is full, and so it's at 8 feet. Okay, so now, remember, you don't want to confuse the top of the tank with how high the water needs to go. In this case, you're just pumping it over the top, right? But if you were pumping it to a height of, let's say, 10 feet, then the distance would be 10 minus y, but we would still be integrating from 0 to 8. All right, so now, how do we carry out this integral? Well, remember, 25 pi times 62.5, that's all a constant. So 25 pi times 62.5, that's a constant, times the integral from 0 to 8 of 8 minus y. So this is actually one that you could evaluate by hand, but then as far as the numbers are concerned, those numbers just get kind of big and annoying, right? So if we were going to do this by hand, we would just leave the 25 pi times 62.5 out there, and then I integrate 8 minus y. So that'd be 8y minus y squared over 2, and then evaluate from 0 to 8. And so I'm going to have 25 pi times 62.5 times 8 minus 8 squared over 2, right? And then minus all of that stuff times 0, right? Because those have 0. So it's really just this, right? So 8 times 8 is 64, minus 8 squared, 64 over 2. So 64 minus 32. So I have 25 pi times 62.5 times, this would be 64 minus 32, so times 32. So that is the number, right? Now, obviously, you could just multiply that times, and what are the units? Well, remember, this is work, so it would be pounds times feet, or foot pounds. All right? So that is slide number 31.